Welcome. This is a second lecture on risk management and insurance. In this lecture, we first discuss semi-logarithmic graphs, and then we go to the main topic of the lecture on present value calculation. Let's first return to equation 11 in the previous lecture. Equation 11 is a continuous growth formula, which you know from science. And it gives us actually a value of some investment at a future date if we have the growth rate R, the interest rate R. Now let's take the derivative of this equation with regard to time. Time appears up here in the power. You probably know how this derivative looks. It's very easy to take derivatives of the Euler number. You just write down the Euler number again with the power. But then you should not forget the chain rule of calculus. You must multiply with the derivative of the power. So the derivative of the power RT with regard to t will be R. So you must multiply this by R. And then you have actually the first derivative. So that's given in equation 12. Equation 12 gives you the first derivative of the Vt function with regard to time. And you see here, so we have actually just the Vt function itself from equation 11, and then you multiply with the derivative of the power with regard to time. Okay, so you multiply by R. So that's coming from the chain rule. The chain rule in calculus is very important, and we use it quite often in finance. So if you do not know it yet, you have to discuss it with one of your colleagues or look it up in a calculus book. Now we can simplify this expression here. V0 times ERT, according to equation 11, is just Vt. So we can use equation 11 again. And so we get this simplified expression. What expression 12 shows is actually the absolute growth rate of our investment, of the value of our investment, Vt. It's expressed in dollars per time period. So it's absolute growth rate. Now in mathematics and also in science, you quite often, or mostly you work with absolute changes, absolute growth rates. But in economists and in finance, we also often use relative growth rates where we express growth in percent. You talk about the growth rate, the annual growth rate of national output, of the gross domestic product, maybe it's 2 or 3% per year, or you talk about the growth rate of the share market, maybe it was 5% in a year, or maybe now, okay, it was minus 10% when the share market is falling. So you arrive at the relative growth rate simply by dividing the absolute growth rate by Vt. So you have the absolute growth rate here. You divide by Vt, you get the relative growth rate, which is just here the interest rate. So if you divide by Vt here and here, then actually here on the right side, Vt will cancel out. Note that also the interest rate or the relative growth rate has actually a time dimension. It has a measuring unit. It's actually 1 divided by time period. So it may be 5% per year if you work with your time period is a year, or it may be 3% per month if you work with a monthly time period. So it's wrong. You read it in quite often in textbook that interest rates have no measuring unit. It's not true. Okay, the measuring unit is actually per time period. Now that's a notation here that we will use quite often for growth rates, for relative growth rates. But it's also used in other contexts, for example, for the inflation rate. Let's now try whether I really can write here. Let's take the pen. So let's assume we have the change in the price level. dpt so that's the change in the price level. That's the absolute change in the price level. Maybe the price level in a year goes from 150 or from 200 to 210. So the change will be 10. But we commonly express this as a relative growth rate. We want to express it in percent. So we divide, okay, by PT. So divide by PT. And then you have the relative change in the price level, which is measured in percent. So maybe the price level goes up from 200 to 210. So it increases by 10. So here it increases by 10. But then you divide by the 200. And you get 5%. It's 5% per year. So it has a time dimension. Remember, so it's 5% per time period, and I use here as a time period of a year. So growth rates or relative rates of change, we can express like this. Sometimes actually terminology is not entirely clear. You see, people speak about growth rates, and then you don't know whether they mean an absolute growth rate, as up here, or whether they mean a relative growth rate, as down here. As I said before, in finance, we tend to use relative growth rates, also in economics, and in science, you very often work with absolute growth rates. So let's go to the semi-logarithmic graph. When a quantity or a variable, economic variable or some variable increases exponentially, then actually non-logarithmic graphs are quite distorted. The slope of a semi-logarithmic graph shows you actually the growth rate in percent. So what you do, you have here the value of our investment, but then you take the logarithm of it, and you plot the logarithm of the value of the investment in a semi-logarithmic graph. Now, you can calculate also this first derivative. Remember, when you calculate the derivative of a logarithmic function, then you just get just 1 divided by Vt, or 1 divided by x, okay, if you do math classes. But then also remember that you have here a chain function again. You see, it's a logarithmic function, and then you have the function v of t. So actually we go to through functions here. V depends on t, and then actually in the end we take the logarithm of that. That's a second function. So you must multiply, because of the chain rule, you must now multiply, okay, here by the derivative here of this inside function, Vt. It's called the inside function. Now, I don't give you here the exact form of this function. So we cannot calculate this dv to dt. If you know the exact function here, then naturally you could actually change it and you could calculate it, and you could really write in here the specific first derivative. So here we are a little bit more general. We just write to dv to dt, but you have to do this. Don't forget this. You have to do this because of the chain rule. What you see here, naturally, we have again the relative growth rate. You see that's the absolute growth rate divided by Vt. So here, here in equation 13, remember that's how the relative growth rate looks. And get the interest rate here. So that's how the relative growth rate looks. So take the logarithm of some value, of some asset value, in our example in finance, takes the logarithm of it, gives you the relative growth rate measured in percent. Now this makes sense if you really think in terms of percent, as for example the share prices. Now if you're investing in the share market, you would like to know how much you earn measured in percent. Maybe you invest $10,000 and then you earn 500, so you have earned 5%. So that's about important for you. Also in GDP, we quite often, that's a gross domestic product, that's a national output, national production in a country. GDP, we think about the growth rate per year or maybe per quarter. Maybe the economy grows by 3% per year or something like that. It doesn't make sense with the unemployment rate. You see, the unemployment rate cannot grow exponentially. When the unemployment rate hits 100%, okay, so nobody works, and okay, so that's just the highest level of unemployment, then it ends. So unemployment rate do not grow exponentially. Also, interest rates don't grow exponentially. They usually are between 0 and maybe 10%, okay, and they don't go higher, except in periods of very high inflation. So it does not make, because interest rates and unemployment rate do not grow exponentially, it does not make sense. Actually, it takes a logarithm of it. But GDP can grow 2% every year or 3% every year. Also, the share market can grow 5% every year. They can grow exponentially. So here it makes sense to take the logarithm. Now here, the top graph is non-logarithmic. It's actually an index of share prices in South Africa, starting here in the 1960s, going up to the end of 2019. So the most recent decline of the share market is actually not yet included here. Here I have the non-logarithmic representation, and down here I take the logarithm. So that's a logarithm of the share price in South Africa. Now the share price may increase maybe 7% per year. It's exponential. So exponential here becomes linear. You see, the growth rate shows up over the entire range of our data. The growth rate now here is a constant, 7%. Now here, it looks as if it grows faster and faster, but actually that's not true. It's just exponential growth with a constant growth rate. So the constant growth rate shows up in the semi-logarithmic graph. The semi-logarithmic graph gives you an undistorted representation of percentage changes. Let's look here in 2008. That was the last big crash in the share market. 2008, here's a share market fell from 60 to 40. The index fell from 60 to 40. So about a third of the capital, 33%, a third of the capital was lost. And that shows up here also in the semi-logarithmic graph. But if you go now back to the 1970s, here we have the first oil crisis, and then here's the second oil crisis. Actually, the share market fell here by a bigger percentage. That's about 40%. You see it's bigger, the decline here than here. You directly see here percentage changes with semi-logarithmic graphs. Now, if you're non-logarithmic, you're okay. You almost don't see it, that the share market fell here. You have the impression here in the 1970s, the share market was very stable. But actually, this little decline here was 40%, and this decline here was only 30%. And that's what you see here very nicely in the semi-logarithmic graph. So that's why semi-logarithmic graphs are very popular in finance. Brokers use it all the time for share prices. We also use it actually when we plot GDP, national output in economics classes. And you have to actually use it when you make graphs over long time periods. You don't have to do a semi-logarithmic graph if you only do it over 3-4 years. But if you have long time periods, then it really matters. Okay, this was the first topic. Let's now move to the main topic of this lecture, which is present value calculation. Let's look at some asset. And that asset gives you just a single, earns you just a single future cash flow. So you own some security or some other type of asset. You own it at time 0, and at time t in the future, this asset gives you some return. So it's just a single cash flow. What is the value of the asset today? So what you would like to know, what you would like to calculate, you would like to calculate the present value V0 when the future value Vt is given to you. Now you also call this actually discounting. And it's very easily done. Just use the formulas from before, formula 6, 7, and 11, and solve them for V0. So formula 6 or equation 6. You see equation 6 gave you the future value when the value today, the present value is given. And now you just rearrange the formula, solve it for V0, then V0 will be Vt divided by 1 plus Rt, obviously. So V0 is just Vt divided by 1 plus Rt. And you can also do it with equation 7 and equation 11, just solve them for V0. Let's maybe just look again, here at the last one, equation 11. So equation 11, V0 will be Vt divided by e to the Rt, and then actually you can write this down as a negative power. So V0 is equal to Vt divided by e to the Rt, and I don't write it divided by, I'm using here a negative power. So we solve for, we are given the future value here, and we solve for the present value. Now this was a very simple example. Let's now consider an investment that does not just give you a single future cash flow, but an investment that gives you actually a cash flow in every future year, maybe at the end of the year. Or just in every future year. We don't distinguish here between beginning and end of the year. I was wrong on that one. Now in the first year, it gives you a small cash flow. Second year gives you a bigger cash flow, and so on. It goes on. And then here at time big T, you then have the final cash flow. What is the present value of this investment or of this asset? Yeah, okay, you have to do the work here. You just have to discount every one of those future cash flow. You take the first one, you discount by 1 year. You take the second cash flow here, you discount it by 2 years. You take the last cash flow here, and you discount it by T, big T number of years. So you must discount each cash flow by the appropriate numbers of years. You just simply apply again one of the equation from before. I think it was equation 7. Yeah, so equation 7, you solve this one for V0. So you have solved the equation for V0, but then you have to actually apply this. You see, you apply just the appropriate number of years. You discount by T years here. So you must discount here the first revenue, the first cash flow, you discount by 1 year. The second one you discount by 2 years. The last one you discount by big T number of years. And naturally you can use, the summation notation. You just have here a general cash flow here in the middle at time small t. And you discount this one by small t numbers of years. So here it's important that you have small t here, and then you sum it up. You sum it up from year 1 up to big T. The first cash flow we get here in year 1. So sum goes from year 1 up to big T. That's a very famous formula. That's a present value formula that all commerce students actually learn in their first finance class. This formula here. Now, what you do then in more advanced classes, let's do something a bit theoretical here. Let's assume the cash flow is continuous. So you do not just get an annual cash flow every year, but you get the cash flow every second, actually even faster. So we go now to continuous compounding, as we did it actually with the exponential growth formula and the Euler number before. So every second you earn a little bit, you get the cash flow, but then you have naturally here a lot of seconds, between 0 and big T. Now the cash flow here is variable. At the beginning, you earn more, and this continuous cash flow falls, and then it again increases. What you do here, you take one of those cash flows here again in the middle at time small t, and you discount that one for small t numbers of years. But then you have a lot of small t's. So you have to sum it up. Sum it up here from 0. It begins at 0 here, and sum it up to big T. So all those discounted. So the index runs from 0 to big T. The index is small t. We have all those cash flows at those times small t. Each one we discount by the appropriate numbers of year, small t, and then we sum it up from 0 up to big T. The two formulas that we learned here are very similar. Remember, here actually we took a cash flow in the middle, small t. We discounted it by small t of years, and then we summed it up. Here actually we begin at 1 in year 1. We sum it up from 1 to big T. All those discounted cash flows. And that's exactly what you do here with the integration. You have a cash flow here at time small t. Cash flow at time small t. You discount it by the small t numbers of years. But then you have to sum it up. You have to sum it up from 0 up to big T. So the formulas, the two formulas are very similar. So only distinction is actually that we also have here this dt. And here we don't have a delta t or anything like that. Now, the dt in integral calculus usually does not matter. But actually it matters in one place when you do so-called integration by substitution. So you should not drop it. So right here, this small dt. So an integral is actually, it's a great way of understanding an integral when you do present value calculation. It shows you what is an integral. An integral is actually just a sum. And that's actually why the integral sign is an elongated S. You see, you have an elongated S here. When Newton and Leibniz 300 years ago, when they invented integral calculus, they wrote everything in Latin, and Newton and Leibniz, they took that actually an S, okay, because an integral, actually one way to understand an integral, it's just simply a sum. Now, it's a sum in continuous time, so we have here actually continuous yeah. So here we have continuous cash flow. Now, if you have a discrete cash flow which arises every year, then you also take an S. Actually, you take the Greek S. You see, that's actually the summation sign here is just this does not work well with actually the pen because then it's so small and it's a laser. So the laser point, let's move back to the laser point. There's no way actually to make the pointer for the pen bigger. Okay, I looked it up. If you know a way, okay, tell me. So that's also an S. That's just the Greek sigma, capital letter. Okay, Greek sigma. Because also here you have the sum. Now let's look at the constant revenue flow, and also we will treat the interest rate as constant. Now, if you have a constant revenue flow that lasts for T years, then we call it an annuity. I have to move back and to the pen. Yeah, okay, here I have it. So here we are at time 0, and then you have a constant revenue flow. It will be the same amount every year up to year big T. That's your big T here. Now actually you call that an annuity. For example, when you retire, you can go to a bank or an insurance company and buy an annuity. You give them money and they will pay you a constant amount of money back, maybe for 20 years during your retirement. Annuity calculations are very important. So maybe you can give them $100,000, and so they will give you something back, a bit more than $5,000 because of interest, okay, every year. Now, if it goes forever, then you call it a perpetuity. So a perpetuity is actually a constant payment which lasts forever. And the ideal here now with so-called ordinary annuities, the payments are made at the end of the year. Now, with annuities, then it becomes a bit easier. We can derive some formulas for the present value. The present value of an annuity that runs for T years, okay, is actually given by equation 20. So here. And if you work with continuous time, then it's equation 21. So you also can think of a continuous annuity, which runs forever. Every second you get something of a little bit. So the E appears here. And then the present value of a perpetuity is actually the same formula, okay, for discrete time and continuous time. Now we will derive those formulas again in this tutorial. You quite easily see that 22 follows from 20 and 21. You see, if t goes to infinity, so now having here a power that approaches infinity, and it's minus. Okay, so this here disappears. This becomes 0. And so I'm just getting v divided by r. That's what I have down here. Same thing here. If you have here, if big T goes to infinity, you have a perpetuity. So then here this power approaches infinity. It's negative, so it's below the bar. So this approaches 0. And you just wind up with v divided by r. Okay, this was our second lecture. Yeah, goodbye.